Hello, everyone. Good morning. My name is Nerea Lezama-Ochoa, and it's a pleasure to be here and be part of this GIS community. This is my first presentation, and today I'm going to talk a little bit about the different use of published sources that are available online for developing species distribution models for protected species. So I'm going to talk a little bit about my background, how to build an habitat distribution model, the different steps that we need. And finally, I'm going to show some examples. So I'm a Basque girl from the Basque Country, specifically from the beautiful San Sebastian, where I did my PhD in Tecnalia, which is a marine institute. One of the main departments are focused on study tuna fisheries and bycatch species. During my PhD, I studied the biodiversity and distribution of different bycatch species, as mobile rays, sharks, billfishes. And to do that, I use fisheries observer data with environmental data to build different species distribution models that I will call them here in this talk SDMs, to understand which are the main areas of importance for some of these bycatch species. So this was the first time that I heard this term and I learned how to do it. After completing my PhD, I went to the IDPC, the Tuna Commission in San Diego, where I did my postdoc, but in this case, very focused on one of these bycatch species that they were mobile rays. In this case, what we used was fisheries observer data, but also artisanal data to try to identify the main areas of importance for mobile rays, specifically for Mobula mobular, using again different SDMs, but in this case, learning and using different algorithms and different methodologies. So it was an advance comparing with the first step of my career. And finally now, I'm in the beautiful Monterey, working for UCSC and NOAA, and a project scientist. And what we are doing is all these SDMs that I learned previously how to be built, we are using the outputs of these models to project the future distribution of different highly migratory species in the California coast. So in this sense, we can use these projections to identify how these species, they are gonna move not only in the temporal domain, but also in the spatial domain. So this is very important step for different economic and implications, conservation implications, and to anticipate for climate change. But what is an habitat model? Okay, I don't know how many of you are like very familiar with this kind of methodology, but an habitat model is simple, a relationship between the presence of the abundance of a species and a set of environmental. We can use different kind of data to build a model. We can get like personal collections, like occurrences that can be obtained during a field sample. For example, I have friends working in Maldives with Monterey, so every time that they go diving, they can take the data and the position of the animal. We can also get some data from longer plant sampling, like voluntaries, from museums, and basically what we use is also to get data online. So there are like different repositories that are online and then friendly user and free that you can use to get the occurrences of the species that you are going to include in your model. The most common one is called Global Biodiversity Information Facility, and also AquaMaps, where you can get environmental data, and Ocean Biogeographic Information System. So I'm just gonna like share this presentation later, so you can just take all the links and you can just like check around. So depending on the species that you are gonna model, you are gonna have more or less data. So anyway, it's very interesting to explore these tools and be able to complete maybe this data with other resources. But mainly, and most of the cases, when we are lucky, we can get access to different data. We can, for some animals, to obtain tracking data. So there are like satellite tags, acoustic tags, and archive tags, and they're gonna give us like a sense of the habitat use of these species, where the species is moving, how is the horizontal profile, in which range of temperature it is moving. The second case, we can build these models using fisheries data, present absence of abundance, like in the case that I used during my PhD and a postdoc. And finally, also, for example, for the marine mammals, we can get sighting data, presence of densities, like based on a specific scientific surveys. In the case of the fisheries data, most of the cases, you usually need to contact the different institutions and apply for different requests to get the data because most of the data is private. But more and more, there are like more public sources when you can get like more raw data, not so specific, but most of the time they are like very available and able to build the models. So one of the examples is you are interested to get data from fisheries, you can go to the different regional fisheries management organization, like in this case, the IDPC, when they have like a public domain with the number of sets, the number of catch for the target species, and the bycatch species, and you can obtain all this data, and this can be used to build the models. There is a new tool since, well, a little bit years ago that is called Global Fishing Watch, and you can obtain also like online and free the different vessel track positions, and you can use this data also to model. There are more and more papers published using this resource. Yeah, the number of users are increasing. Some of them you need to also like to apply, request the data, but I think it's like a huge and a strong tool that is going to be used more and more in the future. For the tracking data, well, the tags, as all we know, they are very expensive, and not everyone has like availability and the resources to be able to have like a good sample size. So still there are more and more databases when you can get tracking data that is already published. This one is an example only for seabirds. MoveBank is a really good one that you can obtain tracking data and positions for different animals or different taxa like seabirds, whales. And here in the Pacific Ocean, close to Monterey, we have the tagging of the pelagic or the tagging program from Barbara Bloch's group in Stanford. Here they have different papers published, and there's la possibility also to get the outputs of this model. This is like a huge database, one of the most important ones. And finally, in the case, for example, of marine mammals, if we are talking about acoustic data, because it's like a huge amount of information, usually it's not available online, but there are like other resources like this one that are examples when you can get sighting data, the presence of densities. So it's like interesting to explore them and see what is available. I think can be also very helpful. Okay, so when we're going to build like a species distribution models, the data that we can obtain from these different resources, they can be, sometimes we are only going to get presence that are the positions where the species has been observed. We are going to get, in other cases, present and absent, for example, some fisheries, where we are going to get the presence and the absence of the species in the sample location. And sometimes we are lucky too, we are going to get the abundance, that is the number of individuals that usually is in weight of the species in kilograms of tons. In the cases that we only have presence, to build a model is necessary to create what we call pseudo absence. That it means like we are going to like create using different techniques, like random simulation of pseudo absence to include in the model. These are not going to be real absence, but they are going to give us like a sense of what it will be the most proxy or the most similar ones to the real absence. This is an example of a paper from my group where they like test different techniques to create the pseudo absence in, I think it was an elephant and blue whale, for tracking data. So I totally like recommend to read this paper, and I'm not gonna go in detail, but just to know that there's a possibility to do. Okay, so once we have our species data, the second question is like, okay, we need environmental data to include in the model. And I think this is the question that it was more like difficult to answer when I was doing my PhD, right? Because we are marine biologists and we are not, most of us, we are not oceanographers, so we don't know like which kind of data where we can obtain it. So the environmental variables that can be used for the different species distribution models, usually they are related to the oceanographic characteristics, like the temperature, salinity, chlorophyll, the topography, or the habitat type. And these environmental variables can be classified as continuous variables, so they can take any value within a certain range, like temperature, for example, or categorical variables. This is only an example to show like the different kind of environmental variables that we can obtain from different resources to build SDMs, like physical variables, as I say, but also chemical variables and nutrients, like chlorophyll, pH, nitrate, etc. So the question is how we can obtain these variables. We can obtain these variables first of all locally. So if you are like sampling a specific place where the species has observed, like research station, you can just get an example of the water and you can take the measure of the chlorophyll, of the temperature. But many of the cases, this is very difficult because some of the species, they are located remotely or very, very far away, and we don't have enough money to sample like enough. So most of the cases to build the SDMs, we use remote sensing data. They are like satellite observations that are coming from atmospheric and terrestrial products like chlorophyll, temperature. And also, once we want to build these SDMs, we can create the models in the future, and we can obtain future environmental variables from ocean models to study climate change different scenarios in the future, but also now is possible in the past. So one of the samples of one of the data sets that you can obtain like species data, environmental data collected locally. One of the samples is the CalCoffee. CalCoffee database is like a program that has been running since years ago in the whole California current, and they are taking information not only about the oceanographic data, but also about different taxa, like marine mammals, seabirds, zooplankton, etc. So this is a really good resource to start and try to have a sense of which kind of data I can get locally. But when we are talking about satellite observations, there are like different resources depending on the quality and the resolution of the data that you need. This is like a list of all of them, but I'm gonna be focused in the first two. So mainly when we build our SDMs, we need, in our case, if it's like a specific small area, like for example, the California current, we need to get like good spatial resolution, but also like like spatial and temporal resolution. So we mainly use the NOAA server and Copernicus database. The NOAA server or the CostWatch server is like a platform when they have all the environmental data that you are gonna probably use. They have like different like programs and courses online where you can learn how to extract this data from the different database, how to relate this data and extract it using R, and also how to plot environmental data like in a map, like here with the chlorophyll in the bottom. Also try to get the exact values for every tracking. So for example, here in the bottom left panel, we can see there is like for a marlin track, we can obtain for each position the chlorophyll value. So it's gonna give us like an idea of how this animal is like tracking different environmental systems. So I totally recommend this to start. I think it's very helpful. They are doing courses every year, online and also in person, and they have like really good tutorials. But the main one that we use is called Copernicus Marine Service. It's a database from the European Union. It has like free access to. You only need to create like an account. From this database, you can obtain like different indicators, different environmental variables. This is the list of them with different spatial temporal resolution. They have like in the past also, I don't know if they have projections, but I think they are gonna have soon. Depending on the variable and the area, you have a specific information. It looks like very overwhelming because a lot of data sets, but the good point is like they have like different scripts, different tutorials also to learn you how to extract the data using Python or again using R. So at the end, you are going to extract the NC file with all the information, and you are going to be able to plot it and see how it looks. If we don't need like so information like day by day or position by position, and we want just to have like a big raster with all the environmental data average, for example, in 10 years, there are other options to explore. Bioracle is one of the main ones. They also have like integration with the R software. So again, you can obtain a script and get all the data you need. And they have different layers that have different layers from the past and also predictions in the future. This is like more simple, but this you need like more global data set and you don't need like a specific spatial resolution. These are very, very helpful. So when we're going to build a model, the most important thing to take into account and think is that you are going to have the spatial scale. You are going to have to choose between different data sets. And the spatial scale has two components. The extension, that is the size of the region where the model is to be run, is not the same as it's going to be the model running the whole Pacific or, for example, in the California current, and the resolution. if our data are, for example, a position of our animal annual, monthly, daily, and the spatial scale. For example, the resolution to study distribution of a turtle in Baja California is not the same as through the Pacific. So there is sometimes we are going to have also like to get high resolution, and depends on the computer and the time that you have, you also have to take into account the computational cost and if it's worth it or not. So for example, this is a case like if we are going to model a species that we have it globally, if we get environmental data at 5.5 degrees, it will be more than enough. But if we want to do it in a specific area, like Baja California, for example, it will be super coarse resolution. In this case, we will need to get environmental data with a lower spatial resolution and more finest. Okay, so we have the species data, and then we were able to get the environmental data from one of the databases. So usually there are different ways to do this, but I'm just going to explain the main ones that we use when we like build a species distribution models using R. We are going to create a database in which each location, each row is going to be the occurrence of the species, where we are going to have, okay, the species in this position, latitude, latitudes, and date. And this is an example of one of the books that I used when I started learning how to build SDMs. That is from Pearson. It's called Species Distribution Modeling for Conservation Educators and Practitioners. And they explain step by step how to build these data frames and how to run all this kind of code in R. So once we have, as I said, the species location, what we are going to do is extract for each location the value of the environmental variable that we are interested to include in the model, and we are just going to paste it in different columns. Finally, once we have created our data frames, we are going to apply different algorithms that are going to be different models with different objectives, pros and cons. And then we are going to estimate and a prediction with a map that is going to give us an idea of where our species is located. So I'm not gonna, in this presentation, be focused on the kind of algorithms, but there are like a different and large number of algorithms applied to classify the probability of occurrence of the species and also the absence. And usually what we use if we are modeling marine species with oceanographic data, we tend to use like general editing models because they are able to relate the species occurrence with nonlinear components. And also, for example, like booster regression trees and random forests that are really good for prediction. But some of them, they have pros and cons again to consider. So this is just like to say that there are different algorithms. Depending on the question that you want to answer, you can use one of another one, and that will be for the next talk, probably next year. But when I started again, like doing my PhD, I found this example of a complete step-by-step example of how to build a model from the library called Dismo, MGCA, and GBM, in which they are going to give you like an example of data frames that you can just like copy and paste into terminal in R, and you are going to be able to download the species occurrence, environmental data, create a pseudo absence in case you don't have, and then feed the model, predict the model, and evaluate the model. So I totally recommend this one to start. And also like try to do like a reflection before doing an SDM, because with my experience, I realized that we're like trying to feed models, I do you know, beautiful maps, and sometimes once you are done, you're realizing that you are actually not answering the main question that you have at the beginning. So after so many years, I think it's very important to sit and have this reflection first. Which kind of data do I have? I have presence, then I need to create a pseudo absence. If I have presence and absence from fisheries, is okay. I don't need to do anything else. Which kind of environmental data I have? Continuous, categorical, which is the resolution of this data and how I can obtain it from the different databases. And what is the question to answer? I'm very focused on the estimation and try to understand the relationships of the species with the environment, or I'm really focused on trying to predict in new areas where I didn't have data. So I need to use like a model and an algorithm that are very, very strong on that. And finally, when you build the model and you get your estimation, you are able to predict, right? And to get these beautiful maps that we like. So there are like different ways to predict. We can predict on the same points just to identify the relationships with the medium. We can predict in areas where we don't have the data. That is going to help us base it on these relationships built by the model to identify new areas. We can project in the past, and also we can project in the future and the different climate change scenarios. But also there are different spatial scales on prediction. It's not the same to predict in a small scale like in the Mediterranean Sea, in the Pacific Ocean, or along a global scale. Okay, and now I think the main question after so many years also like building these models, like, okay, which is the main use of the application, right? We have been having all these models, but we need to understand what we are going to do with this model after, or who is going to use this model if it's not us. For the main use of these models for protected species is for conservation. We are going to use them to try to understand the relationships between the presence of the species and the environment, and identifying the main areas of importance for the species for conservation, like hotspots or specific forage area, northeast area. So these areas can be protected. To do that, we need to build all these models. In the case of fisheries management, these models, they are going to help to create spatial management, like also closure areas, like temporary spatial closure, marine protect areas. And also they are going to help to avoid like areas of risk. For example, EcoCast is a tool created by our group that it was specifically built to try to provide information to the fishermen, to try to tell them in which areas they can go to catch the targeted species, but at the same time to avoid the bycatch species that are on risk. So based on SDMs outputs, they are going to apply different weights and equations. They are going to apply every day, like a map, provide every day a map with areas with high and low risk. And this is one of the main applications. In fisheries also, the outputs of these models have been used to apply risk assessment, so to study the impact of the fishery in one of these species. So we are going to have a value, and it's going to give us, like, generally speaking, like a value of the fisheries, like impacting the abundance of the population of this species or not. More and more now the outputs of the SDMs are included also ecosystem models like Atlantis, Ecopath, Eco-Ocean. So we are not going to have only like a temporal description of the species. Is going to be temporally, for example, the biomass of a fish is going to increase or decrease, but also like spatially dynamic. Okay, so how we can learn all these models? Which are the different platforms that we can use? There are like different ways to do this. I consider like when you are learning, mainly for ecologists, R is the resource. It's a free resource that more of us we have to study, but I know other people doing the same models using MATLAB, Python, GIS. I use R because there are like a lot of resources online. There is a lot of code and examples online. Like here, Stack Overflow is one of the samples. You need just to answer a quick question like how to change the color of the line of the plot, or how to change the scale of a plot. They are going to give you like examples that you can just copy paste and try with your own data. There are also different courses, workshops, and examples in GitHub. So this is like an example of two books that I read years ago. One is like modeling SDMs using GIS and R. The other one is only in R. But there are like different also like resources online and free where you can just have access to courses that you don't have to pay. One is the Harvard University. They have like very basic for beginners, even before you build a model, just to know how to use R. And this is like free. The other one, this is just like you need to pay, but this is like really good one. The people who wrote all the books in R, they have like this platform called Highland Statistics, when they offer specific courses online and also in person in different locations in Europe to learn how to build a specific SDM. So for example, there is like generality models, booster regression trees. They also have like different papers, books, courses, tutorials. So I totally recommend this. I think I went to assist one of these courses years ago when I did my Ph.D. and it's super specific. So they are going to be able to answer all the main questions. And just to finish this presentation, I'm just going to show the main outputs that you can get when you build SDMs using R. Yeah, this is like an example of the different outputs you can get, just to give you an idea that what you can obtain. There are different ways to do it, but I mean, this is an example. So there are like different libraries, first to map and to get the prediction of the species using ggplot2, maps, and raster. The first map is just like overlap of the bathymetry with the position of one of the mobulas in the tuna fisheries. And the second map is the project that we have been working the last 2 years in our lab that is trying to project the distribution of different species. This is Blue Shark. These are the 3 different air system models, GFDL, HAT, and IPSEL. And we can see that in the background, we have the habitat suitability of this species, how it's going to change between the future and the present. In red, we have the habitat that is going to be lost, and in blue, the habitat is going to gain. And then the crosses are all representing the center of gravity and how this species is going to shift from the past to the future. So this is only an example to show that you can actually overlap different metrics in the same maps, like different like core habitat metrics with maps, using that. When you build SDM using these libraries, you can also get this partial plot that is going to give you like an idea of the relationship between each environmental variable with the probability of occurrence of the species. So for example, for this mobula, we can obtain that we have high probability of find this species in areas with low concentration of chlorophyll, for example, in the example B. In the right panel, we can see what we call radar plots. That is going to give us also like an idea of the importance of each environmental variable to explain the distribution of our species. So once we run the model, it's going to give us like this plot to explain that in our case, for example, this species depth that is marked here in pink is one of the most important variables. We can create also animations. So when you run the model, you obtain the predictions. For example, if you obtain predictions day by day, you are going to get able to merge all these predictions, all these rasters and map, and just make an animation using all these kind of libraries. This is like very helpful for presentations, for the stock, for the stakeholders when you want to show the results, and also if you want to identify different, for example, seasonal patterns or annual patterns. In the case of tracking data, there are also different resources, and just want to explain this one. That is a library created by my good friend Robert Bauer. So, and if you are very interested, I can give you his contact. He decided to create these 2 libraries just to plot to create simple analysis when analyzing tagging data. That sometimes is difficult. So they're like, he has some tutorials in GitHub just to show you how to create like different depth profiles and using the SSD information also for the tracking data and be able to plot. He also created this other library called OceanMap that is very simple, but it's only to create maps with raster environmental data and try to overlap information with the tracking data. And again, using the library Extracto, ggAnimate, and RedTap, we can also get the connection between the tracking data with environmental data. So for example, this is an example of our Mobula mobular in Baja California. And along the different seasons, this mobula is going out from the Gulf of California and go to the West Coast. So you can see there is like a gradient and a change of temperature. So you are able to do this, and this is very interesting to see how the different top predators are just tracking the different environmental preferences of an area. And also when you are using tracking data with the library animation, as I said before, you are going to be able to plot of your tracking data, but also like doing animations. And I would like to show this because this is a PhD student, a master student that is going to be soon a PhD student from UCSC. He has been studying thresher sharks in Indonesia. And this is an area that have like a marine protected area only for coral reefs. But 90% of the thresher sharks that are in this area are female. The fisheries are like exploitate them. So they are trying to show in a way that if the marine protected areas are actually like protecting these animals or not. And the results are like most of the time, they spend time inside of the marine protected area, but some of the time they are also like outside. So that means that they should apply different conservations management application for them. Just to show like the last slides, as I said before, You can also build SDMs and include these SDMs in ecosystem models. These ecosystem models have been always used using a specific software, but finally, some people from NOAA, they are creating new libraries like this one called RPath to run the EcoPath model in our software. So that's gonna give us like an idea to share the code between people, and it's gonna be more easy to reproduce the results. If you want to show your results in a paper to the public, in a platform, there is like this really cool library called Shiny App, in which you can plot all the different results that you're obtaining from the models, the radar plots and the time series plot, the maps using, and it's going to give you an idea, and you are going to be able to create like a kind of a website, very simple, in which you are going to be able to decide which species you're going to show and which year and which kind of information you want. So you can learn how to do this in the Shiny app online. You have like different examples, very simple. Yeah, you can just play a little bit with it. This is really cool once you finish your paper. Another way to show the products of your work is using the library Markdown. That is basically to create reports that you can just like share with people, so they don't need to run the code or just like do a presentation. You are going to have, again, a lot of examples just to create your code, or the code that you create to build your model in a specific way that once you just finish it, you run it and you obtain the report. So this is very, I think it's very useful to share with different kind of people. So I think that it's it for today. Thank you so much for attending this and listening. Let me know if you have any question, and I'm happy to see you next time again.